Okay, so I have here actually a double-sided printed, 4 problems dealing with Atwood machines. And so I'm going to solve all of these all in one video. It's going to be fun. I'm going to have fun, and I hope that you have fun. But if you don't, I'm going to respect your decision to not have fun. Okay. So let's just start with the first one, and then we'll work our way through. So here's an Atwood machine. So an Atwood machine consists of, there's lots of different variations of it, but this one has a pulley, and it's a massless, frictionless pulley. It's perfect. We don't have to worry about the motion of the disc right here. It's a perfect disc. And on top, a string runs over the top of that. And on one side I have a 1.2 kilogram mass, and the other is a 1.9 kilogram mass. And I just picked those values. Okay. And in fact, I could actually call this M1 and M2. And then there's a massless, perfect string running over the top. So the first thing is like, if I just hold these two and let go, what's going to happen? I mean, I think that everyone would agree that the 1.9 kilogram mass would, at the very least, move down, and the 1.2 would move up. And I don't think it'd be a stretch to say that the 1.9 actually accelerates down. Now, if it accelerates down, you could actually flick it like that, and it would move up, but still accelerate down, right? Because there's more weight on this side. So let's find the acceleration of these masses. I'm going to start off with a picture. I like pictures. Okay, so here is my Atwood machine. So I have my pulley. I have mass 1. And then I have mass 2. That's an M. Okay, so let's start off with a free body diagram for mass 1. If I draw mass 1, it's going to look like this. There's my dot. I have a downward gravitational force. I'll write it like this. M1G, the vector. And then there's a tension force pulling up on it, and I will write it like this. A little bit bigger. It should be bigger than the gravitational force, like that. Now, I could write my Newton's second law says the net force is MA. And I could break that into 2 parts. I could say F net X is mass times acceleration in the X direction. F net Y is mass times acceleration in the Y direction. But this one is really boring, right? Because if I pick this as my X and this is my Y axis, then there are no forces in the X direction, and there is no acceleration. The acceleration is 0 in the X direction, so it's just kind of boring. I mean, 0 is equal to 0. But if I write the Y equation, it would look like this. So I could say F net Y. It's going to be the tension. The tension's in the Y direction, so I don't need to do a component. But it is positive. And then the gravitational force is in the negative Y direction, so I need to make sure that's negative M1G. And that's going to be equal to M1, and I'll put this as A1. It's in the Y direction, but it's the acceleration of mass 1. So that's an equation. I'm trying to find that acceleration. Let's just put a box around it. Okay, now let's do the same thing for mass 2. So mass 2, here's my dot. I have the gravitational force pulling down, M2G. And then I have the tension pulling up, T. And again, there's nothing in the X direction, so I'm not going to write that down. So F net in the Y direction will look like this. F net Y, it's going to be the tension pulling up, T. The gravitational force is down, M2G. Notice these are scalars, right? Because I'm in the Y direction. That's why they don't have vectors over them. And that's why that's a negative sign right there. And that's going to be equal to M2A2, that acceleration. Box. Okay, so I don't know T, I don't know the tension, I know the mass, I know G is 9.8 newtons per kilogram, that's the magnitude, that's a 9. I know M1, I don't know A1, okay, so, but there is a connection here. I do know a relationship between A1 and A2, because if these are connected by a string, if this one moves up a little bit, that one has to move down the same amount, and so that means if I divide that by time, the velocity of this one in the positive direction would have to be the velocity of this in the negative direction. And if that's true, then I could divide that by time, and the acceleration of these two would have to have the same magnitude. So the acceleration of m1, let's say it's going up, and let's say m2 is going down. So I can say a1, the acceleration of block 1 is just, I'm just going to call it a. And then I'm going to call a2 negative a, because it's in the negative y direction. So now I get the following two equations. T minus m1g equals m1a. T minus m2g equals m2a, negative a. So there's a negative sign right there. Okay. So now we have two equations, two unknowns, and I can solve this. So I'm going to solve, let's solve this second one for t. So if I solve that for t, I can add m2g to both sides, and I get t equals m2g minus m2a. Right, I just added that to both sides. Now I can substitute this into this equation. Instead of t, I can write that. So I get m2g minus m2a. Now I have minus m1g equals m1a. So all I did was put, instead of that t, I put that in for t. Now I have m2g, m2a, m1g, m1a. I want all the a's on the same side. So I'm going to add m2a to both sides, and I get m2g minus m1g equals m1a plus m2a. Yep. Now over here, I don't really care. I'll just leave it like that. I could factor out the g. Actually, I will. I'll factor out the g. Over here, I'll factor out the a. So I can actually say a times m1 plus m2. And now I can divide both sides by m1 plus m2, and I have a equals g times m2 minus m1 over m1 plus m2. And that's my acceleration. Let's go ahead and put in some values. So if I use my values, I have a equals g. I'm not going to put the units. I'm just putting the numbers. 9.8 times m2 was 1.9. 1.9 minus 1.2 over 1.9 plus 1.2. Okay, let me get my calculator. Everyone likes a calculator. Okay, so let's just do it with this silly calculator. 9.8, and you're like, oh, why does this guy hate calculators? I just don't like them. That's all. I'm just saying. 1.9 minus 1.2 close parentheses divided by 1.9 plus 1.2 close parentheses equals. That's not right. I think 9.8 times 1.9 minus 1.2, so it's 0.7, and this will be 3.1. So 9.8 times 0.7 divided by 3.1. Okay, so 2.2 meters per second squared. You know, you can get a number, but I think there's a lot of usefulness in looking at this equation. There's some things that we can check. Number one, what's the units of this, right? So G has units of newtons per kilogram, which is equivalent to meters per second squared. So G has the correct units for the acceleration. Then right here I have a difference in mass, that's going to be in kilograms, divided by a sum of mass in kilograms. And so the kilograms are going to cancel, and I get the correct units. Next, let's think of this. What if I took a ball up here and I dropped it and I released mass 2 at the same time? Just like that. Which one would hit the ground first? Well, the ball would, right? The ball, if I let go, and it's going to have a free fall acceleration of 9.8. But this one has gravity pulling down, but there's some tension pulling it up. So it's not going to have the same acceleration. It's going to take longer for this one to hit the ground. And that's what we have over here. And it doesn't actually, you can see it over here. No matter what we have for M, well, not actually. As long as M2 is greater than M1. Then this number up here is going to be smaller than this number down here. So this fraction, M2 minus M1 is over M1 plus M2 is going to be less than 1. So we have to get that lower acceleration. What if mass 1 was 0? well, then there's nothing pulling up on this one. It's just going to have free fall acceleration. So if m1 is 0, I get m2 divided by 0 plus m2, I get just g. And finally, what if, like I said, what if m1 is larger? If m1 is larger, this is going to be a negative number on the top. But it'll still work. It just says the acceleration of mass 2 is negative. It's actually going to, which I already said it was down, so that means it's actually going to accelerate up, which is what we would think. Okay. One Atwood machine problem down. Cha-ching. Okay. The next one is a half Atwood machine. So this is now the 1.9 kilogram block is on a frictionless surface, and the 1.2 is hanging over the edge. And again, it's a perfect pulley. So let's draw the free body diagram for this situation. Okay, so here's I like to redraw everything. Let's call this M. What did I call that? M2. That was M2 before, so it's still M2. And that one's M1. Okay, so I'm going to draw the free body diagram for M2. It looks like this. So I have the downward gravitational force, M2G. Then the table pushes up on it with the normal force. I'll just call that N. And then the tension pulls. Ropes always pull in the direction of the rope, so it has to be this way. That's that. Now I could write F net Y. Oh, that's the Y direction. It's going to be equal to N minus M2G. But if the block stays on the table, that acceleration is 0 in the vertical direction, so it's just 0. And I don't really care about N anyway, so who really cares? I'm sorry, I don't mean to offend N, the normal force, but no one cares in this problem. Okay, sorry. Don't worry, someone will care about you in the next problem. So now in the x direction, I have something very simple. F net x equals t, and that's going to be equal to m2, and I'll call it a2, just like before. So that's my acceleration of block 2. Oh, I didn't say this. X, y. Okay, now let's look at mass m1. It looks like this. Gravitational force m1g, tension pulling up. Of course, there's no forces in the x direction, so who cares about that? So I can just know it. Yeah, so I can say the y direction. F net y is going to be t minus m1g, because it's in the negative y direction. And that's going to be m1a1. That's the acceleration in the y direction. I'm going to call a1. Now, just like before, if this moves a little bit that way, that has to move up. So the velocities have to have the same magnitude, and the accelerations have to have the same magnitude. And so if this one accelerates in the negative y direction, I could say a1 is negative a, some constant. And this is going to be moving in the positive x direction, accelerating, not moving, accelerating. So a2 is just a. So now I have t equals m2a, and then t minus m1g equals negative m1a. And I want to solve for a. I already have t right here, so I can substitute this in down there. And this equation becomes m2a minus m1g equals negative m1a. Now I can do a little switcheroo here. I'll add m1a to both sides and add m1g to both sides. I get m2a plus m1a equals m1g. And then factor out the a. I get a times m2 plus m1 equals m1g. Divide both sides by that. I get a equals m1g over m1 plus m2. Let's go ahead and put the numbers in. So I have m1 was the 1.2 times 9.8 over 1.2 plus 1.9. So that's 3.1. Where did my calculator go? There it is. Okay. Calculator. On. Clear. 1.2 times 9.8 divided by, what's that? 3.1, right? 3.1. 3.1 equals. So that's 3.79 meters per second squared. Okay. let's just check our number here, right, our expression, because that's what's nice about not putting the numbers in right away, is that I get this expression, I can check it. Does it have the right units? Well, again, I have kilograms divided by kilograms, so that's good, right? And that leaves just g. Acceleration is the same as g. What if I increase the mass m2? What if I have a very, very large mass compared to m1? Well, then the acceleration of this would just be tiny, right? So, and that works, right? Because if m2 is much greater than m1, this is going to be a fraction with a very large denominator, and it would give a very small acceleration. What if m1 is very large compared to m2, or m2 is 0? If m2 is 0, I have m1 divided by m1, so it's just g. So that's good. And then the last thing is if I drop a ball right there, then yes, the ball should hit the ground first. It should have a higher acceleration. Question. Which would be greater? Should this have a greater acceleration than the previous situation with the same masses? And the answer is yes, and it does, right? Because the other one, this mass only does not have a gravitational force really pulling on it. It does, but the normal force also pulls on it. So it just has to accelerate. It doesn't have to fight against gravity. Only this one does. So it does have a greater acceleration. That's a terrible explanation, but that's fine. I want to do the next problem. See how I can do that? It's my video, so I can say, well, I'm just moving on to the next problem. Okay, it looks like the exact same problem, but it's not. This one has a coefficient of kinetic friction of 0.12 between this block and the surface. And so the first question says this is accelerating down, or I'm sorry, moving down. Okay. And then what would happen if it was moving up? So let's do that. Okay, again, I'm going to draw my picture. So that one's M2. I'm going to use the same letters, and that's M1. And let's draw the force diagram for M2. So we have that. We have the gravitational force, M2G. We have the normal force, N. Then we have the tension, T. And then we have a frictional force pulling back this way. I'll call it FF. So the friction force for kinetic friction, if it's sliding, the magnitude FF is equal to the coefficient of friction times the normal force. But that means, aha, we actually need the normal force. We can't just ignore the normal force. So this normal force's day has come in the light, and it's excited to be able to play a part in this physics problem. So if I write this, F net, again, X, Y, sorry about that. I did define my axis. F net, Y is going to be N minus M2G. It's still equal to 0. It still has 0 acceleration. But now I can solve for N, and I get N equals M2G. I'm going to put a box around that, and mostly because I want to emphasize that in this case, the normal force is equal to the weight. But that is not always true. Do not always, I see people do that. They say, oh, normal force is weight. And that's sometimes true, sometimes not true. Okay, so now let's write down the X forces. F net X is going to be equal to the tension minus the friction force, and that's going to be equal to M2. And I'm going to make a quick thing here. I'm going to say this is going to accelerate that way with the value of A, and that's that way with the value of A. Instead of doing, I did it before, I've already done it twice, so I don't want to do it again. So this is going to be a positive acceleration A. And then I can substitute in mu times M2G for the friction force, so I get T minus mu K M2G equals M2A. Box that right there. Now let's go over to my other mass and draw the free body diagram. I have M1G, tension. And then the only thing that's interesting is the y direction. So F net y equals T minus M1G. And that's going to be equal to, remember, it's accelerating in the negative direction. So it's going to be minus M1A. box that. So now I've already used that equation. So I have two equations, and again, I have two unknowns. I don't know t and I don't know a. So let's solve this one for t and substitute it in over here. So this one's going to be, I'm going to add m1g to both sides, and I get t equals m1g minus m1a. And I substitute that in over here, I get m1g minus m1a minus mu k m2g equals m2a. And I want to solve for a. So I'm going to add m1a to both sides. And I get m1g minus mu k m2g equals m1 plus m2 a. Okay, so I shouldn't do that, but I succumb to my desires to take shortcuts, and it's my own fault. It's a weakness I have. But when I add m1a to the other side, I have m2a plus m1a, and I can factor out the a. So I did that all in one step because I thought I was being cool, but that was probably a bad idea, and I shouldn't have done that, and I apologize. Okay, so now I can divide both sides by m1 plus m2, and I get a equals m1g minus mu k m2g, all of that over m1 plus m2. So I could write that, I can actually factor out the g. It'll make it look a little bit better. I get m1 minus mu k m2 g over m1 plus m2. So check the units. Do the units work here? Well, I have kilograms and minus kilograms because the coefficient of friction doesn't have units. So when you multiply it by kilograms, it's still kilograms. And then on the bottom I have kilograms. So yes, I still get units of g. What if the coefficient of friction goes to 0? What if this term goes to 0? Well, then I have this. That goes away. And then I have just m1 over m1 plus m2g. That should be the problem I just solved. Flip them back. Boom, it is. Okay, so if I take the limit as mu k goes to 0, I go back to the other problem. So that's good. Okay, let's just plug in our numbers here. A equals m1, so that's 1.2 minus 0.12, that's a coefficient, times 1.9 times 9.8 divided by 1.2 plus 1.9. Okay, so calculator time. I need to get it in the right position so there's not a glare. I don't know if you can see that very well, but okay, so I have I guess I should do parentheses. 1.2 minus 0.12 times 1.9, close parentheses, times 9.8 divided by, and this is just 3.1. 1. And I get 3.07 meters per second squared. And that actually is significant, right? Because if I look over here, I had 3.79. So with friction, the acceleration is going to be less, which makes sense, right? If there's a frictional force pulling on it, the whole thing's going to slide down. Okay, the second part of this problem said, well, what would happen if this were moving up? And is that even possible to move up? Yeah, you could still have the acceleration down while it's moving up. And there is something that changes. You do get a different value if that happens. You know, suppose I just take this block and push it, and it slides and stops. Maybe it goes back the other direction. I don't know. But there is a difference in this free body diagram. If this block is sliding that way, this friction force is actually that way, right? Because it opposes the motion. So this equation, I should get a red pen. I don't want to redo the whole problem because I want to do the other problem. So that would change. So F net Y, that's the same. That's the same. F net X, this is going to be plus, right? Because now it's in the positive X direction. So down here, this is going to be plus. So now over here, that tension is still the same because that's for this one. I substitute that in over here. This is the same. That's the same. Then I have this is plus. And then I have down here, this is plus. And then, so really I get just that. And that plus. And so you have, and plus. So you have a greater acceleration, which makes sense, right? Because now friction is helping stop that block. Okay. So friction, the direction of friction force does indeed matter. Okay, last problem. This one. So again, I had the same math, 1.9, 1.2, frictionless pulley, perfect pulley, but now it's on the incline. There's no friction, okay? Which way do they accelerate? It's not completely obvious which way it goes, right? If this was flat, then yes, it would go down that way. If it was vertical, then it would go this way. So this is somewhere in between. We don't know which way it's going to go, and that's what makes it so exciting. So let's just, it's okay. We don't have to know which way it goes. We can still do the problem without knowing. Don't ever, just because you don't know doesn't mean you can't do it. That's why you're doing it. Okay, so let's draw a picture and draw a free body diagram. So here's my incline, my pulley. This is M2, and that's M1. Let's start with this one. So, and this is an angle of 28. What did I say it was? Let's call it theta. That way you can do it for any problem. So let's draw the force diagram for M2. So I have the downward gravitational force, M2G. Now I have the tension force and the normal force. Now the normal force is perpendicular to the surface. So here is the surface, that way. So the normal force would be this way. And then the tension force would be pulling this way. So in this case, I'm actually going to make the xy axis this way, x, y. Because if I do that, the block will accelerate in either the positive or negative x direction. And so that means that in the y direction here, it has 0 acceleration. If I make the x-axis this way, then the block's going to accelerate that way. So we'll have an x component and a y component. You can do it. It's possible, but it's hard. Okay, so let's do it the easy way. So that means that I also need this. This angle is theta too, right? Because as this thing goes down, then theta goes to 0. That all makes sense. You can do a little geometry with that, but that comes up enough that you should be able to see that. So let's do the y direction first. F net y. That's going to be the normal force, N, minus, in this case, we have just a part of the gravitational force. It's the adjacent side of that triangle. So this is going to be minus M2G cosine theta. And then the acceleration in the y direction is 0. And honestly, nobody cares. Because, I mean, what do I care about in this? The only thing I don't know is N, but I don't really care about N. Now, if there was friction, you would care. But this is a frictionless problem. So sorry, you don't need that. Now let's look at the x direction, F net x. So here we have the tension in the x direction, and then we have this component of the gravitational force in the negative x direction. So that's the opposite side of this triangle. So it's going to be minus M2G sine theta. And now let's just go ahead and pick. I'm going to pick that this thing is accelerating up the plane. I don't know that that's true, but I'm going to pick that. So let's just say this is equal to M2A, and A is positive. And again, I'm not going to write this as A2, A1. I'm just going to call it A and pick the acceleration. I'm skipping a step, but we did that step twice, so it's okay to skip, according to my rules. Okay, and it's my video, so I can do whatever I want. So there's that equation. We'll put a box around. We don't know T, we don't know A. Now let's go over to mass 1. We've done this exact same thing several times. I have the gravitational force down, M2G. I have the that's a vector. I have the tension pulling up. And then I can write the net force in the y direction, F net y. It's going to be T minus M2G. And that's, this one I'm picking that it accelerates down. So this is going to be minus m1a. So again, put a box. So now I have two equations, two unknowns I need to solve. Let's just go ahead and solve this one for t. So I'm going to add m2g to both sides. I get t equals m2g minus m1a. And now I can substitute that in up here for t, and I get m2g minus m1a. And then I have this minus m2g sine theta equals m2a. And I want to solve for a, so I'm going to add this term to both sides of the equation. I'm going to go ahead and factor out the m2g right here. I can do that. So I'm going to say this becomes m2g times 1 minus, is that m2g? m2, m1, aha. That's, okay, so let's see, this is t equals, that's m1, that's m1. I made a mistake, wow. I'm embarrassed now. That's fine. That's fine. Okay, so let's just cross that out. Okay, so t is going to be m1. That's fine. Okay, so then I substitute that in up here. I'll rewrite that. I get m1g minus m1a equals, no, I'm flustered now. Okay, minus m2g. It's fine because, I mean, how many people make it to the end of a 30-minute video? But if you do, you get to see me mess up. Sine theta equals m2a. Okay, so now I add m1 to both sides. I can factor out that g. I guess it doesn't really matter, but I'm going to do it anyway. So this is going to be g times m1 minus m2 sine theta. And then over here, I'm going to factor out the a times m1 plus m2. And I yelled at myself for doing that before, and I did it again. It's like I don't even learn. I don't know. So now I can divide both sides by m1 plus m2, and I get a equals g m1 minus m2 sine theta over m1 plus m2. And let's put a box. Okay, so we can do some stuff here, because first check the units. Kilograms, what are the units for sine theta? It doesn't have units, it's a ratio. So that's kilograms over kilograms, so that's a good thing. So we have units of g, which is meters per second squared. Now what about this? What if theta goes to 0? If theta goes to 0, then I have, not that problem, I have this problem, right? That is theta equals 0. That's a 0 incline plane. And so it should be m1g over m1 plus m2. So if theta is 0, what's the sine of 0? The sine of 0 is 0. So I get m1 over m1 plus m2. That's really nice, right? That's nice that it does indeed give me what I had before. Is it possible that m1 minus m2 sine theta is 0? Yeah, there's some angle at which these two terms add up to 0. In that case, the acceleration is 0. So you could get this to balance perfectly and it would stay there. And then there's an angle that once theta gets too high, if theta is 90 degrees, actually that's a good one too. If theta is 90, this should go back to the first Atwood machine. So if this is 90, then the sine of 90 is 1. And so I have m1 minus m2 over m1 plus m2, and let's just check. The same thing I had before. Actually, it's backwards. m1, why is it backwards? Oh, I assumed the acceleration. That's why. Because I assumed it accelerated up, right? And the other one, I assumed that accelerated down. And that's fine. Okay, so it could accelerate up, it could accelerate down, and it could just have a 0 acceleration depending on the angle of theta and m1 and m2. Let's go ahead and put our numbers in and see what happens for this particular case. So I have 9.8 times M1, which is 1.2 minus 1.9 times the sine of, what was my angle? 25. That's a 9. Sine of 25. All of that over 1.2 plus 1.9. Calculator time. Put it right here so you can see better. Clear. Okay, so I have 9.8 times parentheses 1.2 minus 1.9 times sine 25. I'm in degrees mode. Close parentheses, divided by, I'm just going to write this as 3.1 down here in the bottom. 3.1 equals. And I get 1.26 meters per second squared. Okay, there you go. That's 4 Atwood machine type problems in under 40 minutes. So it's under 10 minutes a problem. So that's like a bargain right there. Okay, I had fun. Hope you had fun too.